Hello and welcome to the tutorial on building a digit recognizer using the MNIST dataset with TensorFlow and Keras. So we are going to uh, talk about the process of creating the convolutional neural network or CNN for recognizing the handwritten digits. So again, this is a great starting point for the beginners or anyone who is interested in machine learning and computer vision. So the dataset which we'll be using here is called as MNIST dataset. So the MNIST dataset consists of 70,000 handwritten digits. The digits are ranging from 0 to 9, and of course they are stored as images. So that means there are 70,000 images of handwritten digits. So and each image is a 28 by 28 pixel grayscale image. That means it's a non-color image, right? It's not a colored image, right? And because of the simplicity of MNIST, it is often used as the benchmark for evaluating the machine learning models, right? So let us start coding the project. So you should first install the TensorFlow library. So if it is not there, so you can just type pip install TensorFlow. So TensorFlow will be installed in your machine. So the editor which I'm using here is Google Colab. You can use Google Colab or you can use any other Jupyter, like any other editor like Jupyter Notebook or PyCharm or anything else, right? So first we'll import the required libraries. The first important library is TensorFlow. Then import TensorFlow as TF. Right? So TensorFlow is getting imported here. This code is getting executed. And after TensorFlow, I'll need three things. First is data sets, right? So that module is available in TensorFlow.keras, right? So that I'll require for MNIST. I'll be downloading MNIST from datasets. I'll get MNIST from the dataset module. Then I'll require layers module for building the layers of the CNN or convolutional neural network. And then also from the same library I'll require models, right? Models is used to create the structure of the neural network, right? And on that structure, or in that structure, we go on adding the layers, right? So let me import all those three modules, and they are available in TensorFlow.keras. From TensorFlow.keras, import datasets. This will be required for MNIST. MNIST is available in this datasets. Then layers will be required for adding the layers to the CNN, and then models will be required to create the the structure of the neural network, and on that to that structure we'll be adding the layers. Okay, so yes, so we have these three things available with us now. I will need I'll be doing encoding, like one hot encoding. So for that I'll need a module called as toCategorical. So from TensorFlow dot keras dot utils, import to categorical, right? So this I'll use for one hot encoding. So now after the specific models we have imported, we'll load the MNIST dataset and pre-process the images and the labels. So As I have said that there are 70,000 images in MNIST. So I'll be dividing those 70,000 images into training and testing. So near about 60,000 images will be getting into training data set, and 10,000 images will be getting into test data set. So along with images, there are labels of images. Labels means classes of those images. So to which class to those images belong to, right? So we have two things in the data set MNIST. So first is image and its label, right? Label means its class, right? So we'll be downloading those images, and we'll be converting, or we'll be splitting those into training and testing, right? So let's do it. So train underscore image comma train underscore labels. We are dividing the images as well as labels into training and testing part. So this is training, and then we have test underscore images comma test underscore labels is equal to, so data sets. From datasets module, I'll be getting MNIST, right? MNIST dot load data, right? So I'll be calling load data function on MNIST, right? So this will load MNIST, and that MNIST will be divided into training and testing datasets. So yeah, it's downloaded. Now after downloading, you see the train images, the images here are stored as the pixels, right? So array of pixels. The images are stored as array of pixels, right? Now each pixel, right, is taking a value between 0 to 255, right? So the pixel is taking a value between 0 to 255. Now what I don't want that big range. It's a very big range, right? I want that each pixel should take a value between 0 and 1. I want that each pixel should take a value between 0 and 1. So that's why I will be scaling the values between 0 to 255 to a range between 0 to 1, right? So that means I'm making it a smaller range, right? So that is called as normalization. And why it is required? It is required in order to train the model, efficiently, right? So model will learn better. So for that purpose, we need to do normalization of the images, right? So let's do that. Train underscore images is equal to, so I'll simply divide each image pixel by 255.00 because it's a float. So train, then test images also I'll divide, normalize is equal to test underscore images. Yeah, this is train underscore images divided by 255.0, right? So yeah, we have got the normalized data now, right? Now what we'll do, we'll do what is called as one hot encoding of the class labels, right? Or the class names, right? So there are 10 classes, there are 10 labels from 0 to 9. There are 10 labels from 0 to 9. See, our task is very simple. Given a handwritten digit image, we have to classify that image into one of those 10 classes, right? So now what we want to do, we want to do one hot encoding. One hot encoding means, see, let's say there are 10 digits, so we'll have 10 places for 10 digits, right? Now if this is a class, let's say class 5, so only fifth digit will be 1 and all other digits will be 0, right? And if let's say it is not fifth, because we are starting from 0, only sixth digit will be 1, all others will be 0. Now if it is, the image is belonging to class or if it is a class 4, so only fourth digit, I'm assuming we are starting from 1, right? So it is like this. So 0 0 0 0 0. Now if this is 1, that means 0 or yeah 9, right? So this will represent a class 4, right? So this will represent class 4, right? Why 4? Because the this digit is 1, right? This location represent digit 0, this location represent digit 1, this location represent digit 2, digit 3 and digit 4, right? So only if only that particular digit will be 1, others will be 0. That is called as one hot encoding, right? So we'll do one hot encoding and let's see how to do it. So let me remove this. Okay, so train underscore labels is equal to now we'll name them as one hot encoded. One hot, right, is equal to two categorical, and to this two categorical we'll pass train underscore labels, right? And then test underscore labels underscore one hot. So these are the new class names. These are the new class names for training and testing, is equal to 2 underscore categorical into test labels, right? So this will convert the labels or classes into one hot encoded class labels. Now what one more pre-processing I need to do on my data, that is so I need to reshape my input, right? What is my input? Images are my input, right? So train images and test images. So for CNN, the image input will be in the 3D array format, 3D array format, right? So for 60,000 60,000 images, each image is represented by 28 by 28 pixel, and there is one channel, that is because it's a grayscale image, right? So let me show you. Train underscore images is equal to train, I'm reshaping images dot reshape. I'm reshaping the image. How I'm doing it? I'm having 60,000 images, right? 60,000 image. Each image is each image is 28 by 20 pixel, and there is one channel, right? One channel. That means it's a grayscale image, right? 60,000 because there are 60,000 images in train, right? And 28 rows per image and 28 columns, right? 28 rows pixel rows, 28 column pixel 1, 28 columns pixels, and only one channel. It's like you can imagine it's as a cube with 28 as width and 28 as height, and this one as depth, right? One as depth, right? So that's and such 60,000 cubes are there, right? Each cube representing one image, right? Okay, so now this is train images. Test for test also I need to reshape the images. Test underscore images dot reshape. Again same, here we have 10,000 images, right? 10,000, each image is of 28 by 28 pixels, and the color channel is only one, right? So yeah, so we have reshaped our input. Now after reshaping the input, or after pre-processing our input, we'll now build our convolutional neural network, right? So let's so model is equal to, model is the name of our convolutional neural network. Now how will I build it? So models, this models we imported, right? So this models we are using to build this module we are going to use for building the convolutional neural network. So models dot, right, sequential. I want so this neural network will have stack of layers. That means one layer after the other. It's a sequence of layers. That's why it's called as sequential model, right? Sequential, and in this I'll pass the layers, right? Okay, so here I'll pass the first layer, right? First layer of this convolutional neural network is layers. I'll use module layers dot con 2D. It will be a convolutional layer, con 2D 2D. It's a convolutional layer con 2D with 32 neurons, right? And the filter size, right? Because here in this layer, there is an operation called as convolution operation that will be performed. So for that we need a filter or kernel. So size of that filter will be 3 by 3, right? And the activation function, right, which we'll be using for this layer is called as ReLU activation function. And also for the first layer, right, because this is the layer where we are giving input, right, we need to specify the input shape here. Input shape is equal to 28 comma 28 comma 1. So that's the input shape. Input shape only for first layer we need to specify or mention the input shape, right? Then the next layer I'll have is called as max pooling layer. Layers dot max pooling. So convolution layer consists of only two types of layer. Of course, there is one more called as dense layer. So, but we have alternating convolutional layer, max pooling layer, convolutional layer, max pooling layer, right? So these convolution layer basically extract the features from the image, right? And the max pooling layer do the spatial means space reduction, right? Space reduction sort of thing. So max pooling 2D. So to the max pooling 2D, again we need to mention the kernel size or filter. It's again 2 by 2 filter or kernel. Let's add the third layer, layers dot again one more con 2D, convolutional layer in 2 dimensions. It's con 2D means again now here let's take 64 neurons, and the filter size is 3 by 3, right? And then the activation function is equal to ReLU, let's say, right? And then we will add the max pooling, one more max pooling layer, layers dot max pooling, right? Max pooling 2D, and let's again take the kernel size or filter size 2 by 2, and after that one more finally we'll add convolutional layer, layers dot con 2D and to this again we'll be using 64 neurons here. The filter size is 3 by 3, and the activation function again will be ReLU. Activation is equal to ReLU, right? After that, let's say we will add something called as flatten layer, right? Layers dot flatten. Now why this flatten layer is required, so see the output of this convolutional layer will be in this shape, right? In this shape, right? But but the dense layer, which is the layer producing output, so after flatten layer we'll have the dense layers, right? So dense layers requires the output in 1D array format, one dimensional. So this is a 2D or 3D output produced by this layer, convolutional layer. So that output should be converted into one dimensional, right? So 1D array. So that's why we need to flatten the output. So this the flatten layer flattens the output, means the output which is 3D here, right, will be converted into one dimension, right? So after the flatten layer we'll have the dense layer, layers dot dense, 64, there are 64 neurons here. Activation is equal to ReLU again, right? And after that we'll have the last layer, which will be the output layer, layers dot dense, and here I'll have 10 neurons. Why? Because there are 10 classes or 10 labels, that's why I'll have 10 neurons here, right? So that's our model, right? That's our convolutional neural network. So let's execute this. Yeah, we have built the model successfully, right? And then we will compile our model, right? After building the model successfully, we need to compile the model. So in compiling the model, we specify what optimizer we are going to use. Optimizer is important for training the neural network. This optimizer, because of the optimizer, the neural network weights get updated, right? We'll also mention the loss function which will be utilizing here. Then then we'll also mention what is the evaluation matrix, performance evaluation matrix we are going to use, right? So that's all we will mention in the compile, model.compile, right? So model.compile. So to this we'll pass optimizer. So we can use Adam or SGD. So we'll use Adam here. Adam is the name of the optimizer, and then the loss function will be equal to, let's say, tf dot keras dot categorical cross entropy. So this loss function is normally used for multi-class classification problem, and this is a multi-class classification problem. So categorical cross entropy, and from logits equal to true. That means when the the activation function in the output layer is not softmax, right? So the output function here is activation function in the output layer is not softmax. So that time we need to keep this logits equal to true, right? That means the input to the loss function is not probabilities, but it's digits, right? So then after that I need a matrix is equal to accuracy. Will use accuracy, right? So let me execute this. So model.compile, yeah, just a moment. Okay, module TensorFlow.keras has no attribute categorical cross entropy. Okay, so let us say we'll import directly from keras.losses. Losses dot, let me check now. Yeah, okay, now it's working fine. So after compiling the model, we should do training of the model, right? So we'll do training of the model. So for training, so model building, model compiling, and model training, right? So history, this history will record the accuracy of the model per epoch, right? So model.fit is the training, right? So for training we call fit function on the model, and to this fit will pass the train data, train images, right? We'll also pass the labels of those images, but one hot encoded labels will pass, and then we'll mention the epochs. Epochs is equal to 10. That means the neural network will see the entire input, training input, for 10 times, right? So it will get trained for 10 epochs, right? And then validation data is equal to test underscore images. So these will be used for validation. Test underscore labels underscore one hot, right? Okay, so this will train our model for 10 epochs, right? And let's see what happens. So model is getting trained. This is epoch 1. So let's see. The loss is getting decreased and the accuracy is increasing. You can see here, right? Okay, so I'll show the training for one epoch and then I'll pause the video and directly show you the output. Okay, epoch 2 has started, so let me pause the video so that we can cut the duration of the video. Okay, so almost training is completed. The last epoch is going on, 10th epoch. So you can see each epoch has taken approximately 60 seconds of time for getting trained. And you see loss here, it was 0.15 and accuracy was 0.95, that is 95%. Over the epochs the loss is getting decreased, right? So loss, you can see here, it's 0.0110 and accuracy is 0.9965, that is 99.65%. And finally, in the last epoch the loss is very less, which is 0.009, right? And whereas the accuracy is approximately 99.7 percent, right? So that's how the model accuracy is improved over the epochs, right? So this is validation loss and validation accuracy, and you can see validation loss is 0.0274 and again validation accuracy is again over 99%. So now what is this history? This history object is written by this model.fit function after the training, and what it contains, right? So this history object contains the record of the training metrics, that is accuracy in this case, for each epoch, right? So see, the object history object is an instance of the history class in Keras, right? And what it contains? It contains the directory named as history, right? Which holds the metrics computed during the training phase, and these metrics typically include loss and accuracy for each epoch, right? And if we have a validation data set, it will also like here we have a validation data set, it will also include the validation loss and validation accuracy for each epoch, right? Now how to use this history object, right? So this history object can use for accessing the data, right? We can access the training data, training and validation matrices or metrics from the history dictionary, right? So if you want to access accuracy, right, you will say history of accuracy, right? And if you want to access the validation accuracy, you will say history of validation accuracy, right? And we can also plot these metrics for better visualization, right? We can create a plot of training accuracy versus validation accuracy over the epochs, right? So, and which can help us in understanding how well the model is learning and whether it is overfitting or underfitting. So let me just show you how to plot by using this history object, right? So I need matplotlib for plotting. Import matplotlib dot pyplot as plt, right? So I'll need matplotlib, right? So and then I'll plt dot plot, so history dot history, right? So I want to plot accuracy, right? And then I also want to plot the validation accuracy, plt dot plot history dot history. This history will contain accuracy as well as validation accuracy, right? And then we also want to label our plot like plt dot title. Plt dot title is model, let's say, accuracy. And then we will give label to x-axis and y-axis. So plt dot y label is accuracy, right? And plt dot x label is epochs, right? How accuracy is increasing over the epochs. And then we'll give legend as train, comma test, right? And location is equal to upper left, right? So yeah, and with that plt dot show, right? So this will plot the validation accuracy and accuracy of the model, right, against epochs. You see here, right? So legend is and legend, okay, yeah. So you see this is epoch and accuracy, right? Accuracy, how accuracy is increasing over the epochs, right? So again, upper left is not a valid value for lock. Upper left, there is no underscore here, okay. Let me run. Okay, now we got it perfect, right? So you see this is the training, right? Accuracy of training data, how it's increasing over the epochs, right? So after the first epoch it was around 95%, and then after second epoch it was around 99%, and then it kept on increasing till the last epoch. And then for validation, it's like to in the beginning epoch it was better at second, but it's decreased during third and fourth epoch, and then again steadily increased over, right? So you can compare this validation accuracy and model accuracy by using this history, right? So that's the use of history, right? Okay, so after that we are almost done. Finally we'll you know evaluate the model performance, right? So by printing the test loss and test accuracy, right? So test loss is equal to test loss comma test accuracy is equal to model dot evaluate. So test underscore images, comma, test underscore labels, and which are one hot, right? And we'll keep verbose is equal to 2, means how much input, how much contents you want to see per line, right? And after that we'll print uh, slash n on new line we would like to print test accuracy, that is test cc. Okay. Yeah, test accuracy we are getting 99.26, that is 99.26 percentage, right? So it's 0.9926 means 99.26 percentage, right? So yes, that's it. We have just build and train a digital recognizer using the MNIST dataset. So this is a great foundation for you people to diving deeper into machine learning and computer vision. So thank you so much for watching and all the best.